Okay, so the next question that we got on the menu today is how do we prove the equation for kinetic energy, which is KE, kinetic energy, equals 1/2 mv squared. Okay, so we're going to try to prove this, and we're going to prove this with the equation for work. Now, work is the how you add energy to it. So if I push on a bowling ball and it starts rolling, that means I exerted some work, which means I gave some kinetic energy to that bowling ball, and then it's rolling away. Okay, so the equation for work, W, is equal to F multiplied by D. So this is force multiplied by displacement, and this is work. It all works out. Okay, cool. So we know that force from Newton's second law is F equals mass times acceleration. And let's think to our kinematics equations. We have a kinematics equation that is like this. The final velocity squared minus the initial velocity squared. Just going to verify that. I think it's down here. Yep. Is equal to 2AD. D being the displacement. The D, this D, as well as this D are the same D. Okay, so this is our kinematics equation. And let's try to substitute out A so that it is let's substitute out A so that it is just alone, or isolate A is probably a better way to say that. So A is going to be equal to V squared over U squared divided by 2D. Okay? Now let's put that equation into F equals MA. F equals M times V squared minus U squared over 2D, because that's A. And then we can take this F and put it into the work equation. So W for work is equal to M multiplied by V squared minus U squared, the initial velocity, over 2D, and multiplied by D out here. But you see, we got a D on the upstairs and a D on the downstairs of the fraction, so they neutralize each other. And we are left with this. W equals M V squared minus U squared over 2. Now you see that the only difference between this W and the kinetic energy up here is that U squared, or U, has to be 0. And if U is 0, that just means that we're starting from an initial velocity of 0. So start at rest, and it will be U equals 0 meters per second, and then we apply some work to it. However much we increase the velocity by, that's how much, like if we're putting in work, like we're applying a force to the system and it's going to increase in velocity. Once we stop applying a force on it, we will no longer have any change in the velocity, and the velocity is going to be 0. No, I mean the u is going to be 0, but the velocity is going to be constant. So so if we're starting at rest, we have W equals work is equal to mass v squared minus 0, but that gets like ignored, over 2. So this work becomes kinetic energy. Okay, I'm applying a force, I'm giving energy to the system. Since I'm starting it at rest with u equals 0, however much I increase the velocity by is however much I increase, like the amount of work I give is the same as how much kinetic energy that it gains. And you can see if I started at rest, I give it a little push, I apply a force over a distance, I apply some work on it, I added work to it, so that means that work, that energy from the work is converted into kinetic energy. That you know, and it follows the exact same equation. So this becomes KE equals mv squared over 2. So the main clues that you want to use is to know that work and energy are tightly related. They're always equal. Conservation of energy, don't forget that. Then we got the work equation. So we know F equals ma. We used our kinematics equation to get a nicer, to isolate A, and then started at rest, and you know, it all works out. Yeah, so the above solution here is good. Cool. Awesome.